let's give you a quick review for previous class. In previous class, actually we talked about the heterogeneous reactions. In order to get the overall rate equation of your interesting heterogeneous chemical reaction, we need to consider mass transport between different phases and reactions. So, for example, if you have a solid carbon react with the gas oxygen, and it will generate carbon dioxide, right? So in these heterogeneous reactions, we can separate this process into 3 steps, which we call a series reaction. In the beginning, the oxygen. So let me draw something. If I try to plot the oxygen concentration and show in red, okay? Or red, probably I change the color. So, okay. So the oxygen concentration will remain constant in gas phase. And as we mentioned, when gas, there's the film layer in between 2 phases, and this film layer or transport layer will be served as a diffusion layer. So for example, like we have oxygen here, the oxygen need to diffuse through this transport layer to arrive at the surface of solid carbon and start the reaction. Okay, so you got the transport layer and also the reaction. And as we mentioned before, you can use electrical circuit to model this heterogeneous reaction. So in electrical circuit, we have a driving force here. So the driving force here actually is a concentration gradient of the oxygen serving a driving force. Here, concentration of oxygen, or you can see the partial pressure gradient of the, because it's a gas, so probably it's a partial pressure of the oxygen gradient of the driving force. And the current here is passing, actually oxygen diffuses through the film layer and also reactions. So the flux for transport should be the same or flux for reaction. And we assume that, so this is reached steady state, means how much oxygen be transported through the film layer equals to how much all this oxygen be react with the solid carbon. So this flux should be equals to. So it's similar to with the current, right? When current passing through different resistance, inside the electrical circuit, the current are the same, right? Same current passing through different resistance. So here we also have the flux passing through different layer or different process, transport and reaction. And regarding to the resistance, because we have 2 processes, right? It's transport and also reaction. So we use the RT to represent the transport resistance to quantitatively describe how fast this transport is. And we also use the RR, reaction resistance, to represent how fast this chemical reaction is. This is all happen on the surface. So the same idea, we have a driving force is the concentration gradient of the oxygen will drive the oxygen flux passing through the film layer and reaction. And for each process, means the transport and reaction part, we have the corresponding resistance. Okay, and if you have this concept, let's move to next slide to give you an example and try to demonstrate that this heterogeneous reaction really can use the electrical circuit to model it. So what we have here is we have a liquid-solid reaction. We have a liquid A react with solid B and generate liquid R. So there are two phases involved in these reactions. So this belongs to heterogeneous reaction. So when we try to write down or plot the figures to represent these reactions, probably we will write like this. On your left-hand side, we have a bulk liquid A. On your right-hand side, you have solid B, and in between is a transport layer or film layer, and here we call it liquid film layer. Okay, and here just a remind, because solid B, molecular B is not going to move into the liquid, so this is a solid B, right? So always stay here, and A, the molecular reactant A, when you try to write down the concentration of reactant A in the liquid main body will remain constant. So we call it a CAL. It's a concentration of reactant A in liquid main body. And when this A molecular diffuse through the liquid film, if there's no resistance in the liquid film, which implies that the concentration remains constant here, so it will be, the curve will be shown like this. But when A arrives on the surface of solid B, it will completely consumed by solid B. So the CAS, the CAL equals to CAS in this condition, right? But finally, because A will be completely consumed by solid B, so the Ca2 will become 0. So the curve will be shown like this. It can be like this, right? But this means actually we don't have resistance in the liquid film. Also means that the transport of reactant A in liquid film is very fast. So we cannot observe the concentration decrease inside the liquid film. But however, on the other hand, if the transport of reactant A in liquid film is not fast, it's slower, so which implies that there's a flat. Okay, so it implies that if there's the transport is not as fast as previous one, so as long as it has a resistance inside the liquid film, the concentration will decrease as a function of location. And when it arrives on the surface of solid B, the concentration becomes CAS, means on the surface of solid B. And after react with B, then we assume it will completely consume at this interface. Okay, and the slope here can be, as I mentioned, if this transport is quite fast, so we don't have the concentration remain constant, right? But if the curve show like this or this, depending on how fast molecular A diffuse into or diffuse through this liquid film. Okay, and additional, the thickness of the liquid film is delta X. So you have already drawn this. So we try to answer. Don't forget, our question is: can you formulate the overall rate equation for this heterogeneous chemical reaction? But based on the knowledge you learned from lecture 6, probably you will write down the reaction. So consumption rate of reactant A will be equal, and we also assume this reaction belongs to first order, so probably we'll write down like this, right? The flux. Okay, oh, I forgot to mention one thing. Yes, and the flux should be equal, right? The flux of reactant A passing through liquid film will be equal to the flux of reactant A react with solid B. So, and back to here, if I want to ask regarding to the overall rate equation of these heterogeneous reactions. So you probably will write down JR is the consumption of reactant A per interfacial area equals to, and minus means the consumption rate, and equals to rate constant times the concentration CAS, right? This is can be considered as the overall of rate equation. But now, based on this equation, we don't have any idea about what's the CAS. It is non-measurable because it's a concentration reactant A on the surface before reaction. So it is a non-measurable term, right? So in order to answer the rate equation of this heterogeneous chemical reactions, so we want to know what's the CAS. So how can we do that? So we still have the other information is when it reaches to steady state, we know the flux will be the same. Okay, so the following step is, based on this clue or this information, we can substitute CAS in terms of CAL, which you know that because this is the concentration reactant A in liquid phase. You end it right in this reactor. Okay. Okay. So next, let's try to formulate the flux of reactant A passing through liquid film. So flux, so it's a consumption rate of reactant A per interfacial reaction area. It's a double prong. O will be equals to minus diffusivity concentration gradient. Concentration gradient here will be CAS minus CAL divided by delta X here. Okay, and next we call this diffusivity divided by the thickness of liquid film as KL, which is a transport coefficient. Transport coefficient is an indicator to tell you how fast or how slow this molecular A diffuse through this liquid film. If you have larger KL means diffusivity is larger, means diffuse faster. Okay, if you have a small KL means the diffusivity is slow, diffusion is quite slow. Okay, so now you have formulate the JL here, and this is the one I just mentioned. You formulate the JR reaction rate equation for this chemical reactions, and when it reaches steady state means the supply of reactant A will be equals to consumption of reactant A at the surface of solid B. So this one will equals to this one, means this will be equal to this. So in this case, you can get the relationships. You can get the CAS in terms of CAL. So now we can substitute CAS in terms of this term. Substitute here. So back to the rate equation we want is K double prime times this value, and become here. And we divided by K double prime and KL together on the top and also the bottom, so you will get these results. So let's pay attention on this result. On your left-hand side, this term actually is a consumption rate of reactant A. It's a flux equals to concentration of reactant A in liquid main body divided by the reciprocal of KL plus the reciprocal of rate constant. And this is quite similar with the electrical circuit one, because for the electrical circuit flux, you have driving force, right? So the driving force is CAL, because CAL, the driving force for this example actually is the concentration difference, right? CAL minus 0, so it's a CAL V equals to I, similar to flux, times R resistance. And here resistance, you have two terms in series, so will be include your transport resistance plus the reaction resistance. And regarding to a resistance, if you have high resistance, which means diffusion is slow, right? So the transport coefficient actually is inversely proportional with the resistance. So reciprocal transport coefficient, the idea will be equals to resistance. So if you have a larger KL, means transport faster, right? And resistant. After you reciprocal of this term, it gets smaller. And this is also the resistance, which is the reciprocal of the rate constant. V equals to I R, total R, and you have RT and also R. Okay. And I just want to rewrote this K over rho to become here. So here is the overall resistance. Okay, is a reciprocal of K over rho. So we got this results. This will be equals to this plus this. But this figure is just show you after series deviation. I already convinced you that these heterogeneous reactions involve transport and reactions can be right as a driving force times equals to the flux times resistance, and inside resistance one we have transport plus reactions, so you have transport resistance plus reaction resistance, and regarding to a resistance is a reciprocal of transport coefficient or rate constant. Okay, and after class actually some people ask me about how about if the case if it is not completely consumed at the surface of solid B, what will happen? So based on the Ch7 principle, if you still have remaining molecular A or accumulation of molecular A at the surface of solid B, then you cannot formulate this relationship. And by the way, this kind of the concentration of reactant A increase to it will destroy the chemical equilibrium under these situations. So under that situations, it's difficult to you to estimate the rate equation for this type of heterogeneous chemical reactions. So for experimental point of view, in the beginning, if you want to deal with this type of reactions, I would suggest you to add the tiny amount of reactant A to make sure the consumption of reactant A on the surface of solid B will be equals to consumption of reactant A on the solid B is almost consumed completely. Under that situations, then you can easily formulate this. You can easily to get this rate equation and estimate this overall rate equation. Otherwise, it's quite difficult to deal with. Okay, so if now you already have some ideas, so let's move to this V equals to IR. Okay, so next, if you already have some ideas, so let's move to the other case, which involve three phases: gas, liquid, solid reaction. So So what we have here is we have a pure gas reactant is bubbling through the liquid containing suspended catalyst particle in a slurry reactor. So I draw this cartoons to represent these situations. If we have a pure reactive gas A bubbling through this liquid contained with suspended catalyst in a particle in the reactions. So gas A is going to diffuse through the liquid to arrive on the surface of particle and start its chemical reactions. So in order to estimate the overall rate equation for this type of conditions, so I try to enlarge this reaction region, and try to draw the figures like this. We have gas A at your left-handed side, and right-handed side we got the solid catalyst, and in between we have a liquid. So you have a gas, liquid, and solid. And as we mentioned before, as long as you have two different phases, in between there's for sure has a film layer. And in this case, and by the way, and this is liquid and this solid, so we also have a film layer in here. So now we have two film layers. But in this case, in the beginning we focus on the reactant gas A, right? So near the gas, we call the gas film. And this is this is near the liquid, so we call the liquid film layer. And when we try to draw the concentration of reactant A in the gas phase, it will be the CAI, and the gas A will diffuse through gas film, so probably the concentration will decrease as a function of location. And when it enters the liquid main body, so we assume the transport of reactant A is very fast, means the K is approach to infinity. Okay, and reciprocal of infinity is 0, so the resistance is 0, so I can draw the concentration remain constant in the bulk liquid. And when the molecular A again passing through the liquid, diffuse through the liquid film, so probably concentration will decrease again as a function of location to arrive on the surface of solid, and the concentration here will be CAS. And the same idea, after react with catalyst particle, and the reactant A was completely consumed. And in this two film layer, we use the KAL transport coefficient to represent how fast of reactant A diffuse through, and also use a KL2 to represent how fast of reactant A passing through, diffuse through this liquid film. Okay? So based on this, if you want, the question would be, could you formulate the consumption rate of reactant A or overall rate equation, right? So in the beginning, probably you will directly write down the one is the consumption rate of reactant A equals to rate constant times CAS. This is quite easy to you to formulate, but the same idea. It's difficult to directly measure the concentration of reactant A on the surface. So we are going to use the other tips to substitute CAS in terms of CAI will be when it reaches steady state, which means the reactant A how much the reactant A be transported through gas film, main body, liquid main body, and liquid film. This reactant A will be completely react with solid catalyst. So the JAG will be equals to JAL and equals to JR. So now we try to formulate the JAG. JAG actually is a KL1 times CAI minus this one. And this is KL2 equals to KL2, and this CAL minus CAS here, and the JR actually is the rate constant times CA is. So this are the same when it reaches steady state. Okay, so this relationship will help you to substitute CAS in terms of CAL and CAI. Okay, so how to do that? So you use equation 2 and 3, you can get the CAS in terms of CAL, and you directly use this term to substitute here. So RA double prime equals to K double prime times this one. So now you got the CAL, but it's still not easy to measure the CAL inside your experiments, right? So I'm going to use these 3 relationship to get the CAL in terms of CAI. How to do that? You just use a list to substitute CAS, and only one you only left the CAL and CAI, so you can express CAL in terms of CAI. Okay. So now you have this relationship. So let's rewrite these equations. K double prime CAS, so B equals substitute here, and here this term you substitute with this term. So after arrangement, you can get the consumption rate of reactant A can show like this. Will be the same idea, right? Driving force CAI minus 0, driving force, flux times total resistance. Total resistance included each layer, the reactant A diffused through each layer, right? This layer will be a reciprocal of KAL, so KL1, and some people probably will think about how about this layer? Yes, as I mentioned, K is approach infinity, so 1 divided by infinity, almost 0, so you plus this is turns 0, and this is 1 divided by KL2, and this is 1 divided by rate constant K double prime. And this part is you also can write like this, equals to total resistance. Okay. Okay. So if you don't have any idea, also if you don't have any questions, so let's move to the examples to end these sections, which is the fluid solid reactions. So the example here is we are going to talk about the oxidation of silicon substrate. And in semiconductor industry, there are 2 methods to have to form the silicon dioxide. The first method we call the dry method, which means when you flow the oxygen react with silicon substrate at a high temperature, then you can get the silicon dioxide form on the top of silicon substrate. And the wet method actually is you flow the water vapor react with silicon substrate at high temperature, and you will grow the silicon dioxide and on the top of your silicon substrate and in the meantime you will generate some hydrogen. So the question would be, which method can have a higher growth rate of silicon dioxide? Higher growth rate. So in order to do that, so you can expect it higher growth rate, so I need to know the thickness of silicon dioxide, right? So for this case, I try to draw the figures or cartoon to represent these situations we have. So I draw the left-handed side, we have oxygen, and before reaction happens, silicon substrate is here. Okay, x equals to 0 actually means this is a silicon substrate before reaction happens. Okay, so when I try to plot the concentration of oxygen, so it will be C concentration of oxygen at infinity and remain constant in gas phase. And because this is a gas and this is silicon substrate solid phase, so in between there's a gas peak layer. So probably the resistance, there's some resistance in the gas phase, so you can observe the slightly decrease in the concentration of oxygen, and when it arrive on the surface of silicon substrate, the concentration will drop to Cs. And due to the silicon substrate, when the oxygen want to diffuse into the silicon, there's we call the solubility of oxygen inside this oxide layer. We call it Cs prime. And as you know, when you have a silicon dioxide, and thickness will get thicker and thicker to delta. And when you try to growth more silicon dioxide, which means that the oxygen need to diffuse through this oxide layer to arrive on the surface of the silicon substrate to oxidize the silicon atoms beneath the surface, right? Probably up here. So the concentration of oxygen will decrease from Cs prime to Ci. And here, the delta actually means the thickness of silicon dioxide layer. So based on these descriptions, we know the driving force for sure will be related to here, right? And also the flux should reach, we need to assume it reaches steady state. So Jg equals to Jd equals to Jr. Okay? So let's try to formulate what's the Jg is a transport flux. Flux of means the transport of oxygen in the gas film. So the Jg is a rate transport coefficient Km and C infinity minus Cs. And regarding to the flux passing through oxide layer, also the Jd, we call it the Jd, and instead of directly use the transport coefficient, we use the diffusivity divided by delta thickness of dioxide layer and Cs minus Ci. Here, why we don't use the transport coefficient Kd to represent here? Due to this is not a constant, right? Because the thickness of dioxide layer is going to increase as a function of time. So it is measurable, so we put here instead of a Kd. And regarding to a reaction at the interface here, you can write down the rate constant times the Ci, the concentration of reactant, concentration of oxygen. And when it reaches steady state, this will be equals to this, equals to this. Before we move forward, I want to highlight 3 important things. It turns out that in the beginning, at the short time, which means we only have negative oxide layer grow on the silicon substrate, means the oxide layer is quite thin. Then this reaction should be dominated by reaction process, right? But as the reaction time for a long time, after a long time, the thickness of oxide layer will get thicker and thicker. So that will the oxygen will spend more time to transport through this oxide layer and react with silicon atoms. So in this case, probably the rate limit step or process or step will become the diffusion process, right? So this is some concept, just like you use your logic to make assumptions or make a guess, something like that. But this is just a roughly assumption or a roughly guess. So you need to I would suggest you to do more quantitatively estimation. So next I'm going to show you how to do that. In order to simplify the cartoon or situations I just draw to you, we assume the Km transport coefficient in this gas fin layer is very fast, which means we don't have any fin resistance. So means the concentration remain constant. So means the C infinity equals to Cs. And we also assume there's no interfacial resistance at x equals to 0. Interfacial resistance means Cs equals to Cs prime. So now this equals to this equals to this. So we try to simplify our situations. So now we don't need to, there's no concentration gradient here, so we don't have Jg. So now we have Jd equals to Jr. So we put the Jd equals to Jr, show like this. Okay? So in this case, we can write down like this, and this equation can help you to get the Ci, the concentration of reactant A, or reactant, the concentration of oxygen at the interface in terms of Cs. You can measure. Cs is a measurable thing, right? You know the Cs because it's a concentration of oxygen in the gas phase. But Ci is now non-measurable, so now I already use this equations relationship to get the Ci as a function of Cs. So I can substitute Ci, right, in terms of Cs. But this flux doesn't give you more quantitatively description because it's very difficult to us to measure the consumption rate of oxygen in your experiments, because usually we'll flow lots of oxygen in to oxidize the silicon substrate, right? So and the only parameter we can measure in this oxidation process will be the thickness of the silicon dioxide layer. So I want to play a trick here. The J oxygen actually is a Jd. Okay, J oxygen can also express like this. Let me expand here. I want to try to link this flux J oxygen with the measurable delta is the thickness of silicon dioxide layer. So what I'm going to do is here, the delta times A is the area of the silicon substrate, you times the increase in thickness of silicon dioxide. This part actually is the increase of silicon, increased volume of the silicon dioxide, and you times the density of the silicon dioxide, you got the increased weight of silicon dioxide. This is in weight, increased weight of silicon dioxide, or generation weight of silicon dioxide. Okay, then flux, you mean you need to divide it by the area and time, but this is the weight of silicon dioxide, right? You divide it by m. So what m means is the one oxygen the mass of silicon dioxide formed by one molar of oxygen. So this is the mass of silicon dioxide, and I divide it by m. This tells you how many molecules of oxygen you use or consume to get this amount of silicon dioxide. And this is also flux, right? So it will be per time per area. So based on this idea, you delete this term, so you will get this is the J oxygen is a Jd. So we put the Jd this term here and substitute this term. K capital R times this term, put Jr, then you will get this relationship. And just Kd, as I mentioned, Kd is not constant. You just recover, then substitute this as a diffusivity divided by delta. And now you have these equations. Okay, so it's a partial delta, partial t. So we take the integral on both sides, and the t is from 0 to time t, and the delta is from delta I from delta. Delta I is initial thickness of silicon dioxide. So as you know, the silicon substrate always have a thin layer of native oxide, so the thickness will be the delta I. So based on these equations, we can compare with this typical equations and you can get the, based on this, you can get the delta expressed like this, and inside we have AB, and tau will be shown like this. So delta is the thickness of silicon dioxide layer, is a measurable one, and T is the time. So we have the thickness of silicon dioxide as a function of time, and also A is related to diffusivity divided by Kr, and B is related to diffusivity Cs, M, and rho. And T tau actually is related to the initial thickness of silicon dioxide layer, and also have and plus this and this. So I just copy these results, and we want to discuss more about the measurable thickness of silicon dioxide as a function of time. Why this is so important? Because our questions is ask you about which method can have a higher growth rate of silicon dioxide, means this will be higher, right? So I just copy these results to next slide. And in order to exactly know the delta as a function of t, so please take a look on the solutions here. You can simply separate t plus tau. If t plus tau is quite smaller than a squared divided by 4b, which means this term t plus tau times this value will be quite small. So as I mentioned before, you use 1 plus x, and this is 1/2. If x is very small, then you can rewrite as here, right? 1 plus. So here you use 1 plus 1/2x, and this will be 1 plus 1/2x, and you minus 1 here, so only 1 you are left is 1/2x, and 2 divided by, or 8 divided by 2 here, and 1/2x. So after delete the 2 to 4 here and a here, so you got this. So the thickness of silicon dioxide proportion with b divided by a, and b divided by a, you deleted the d, so you got the proportion with rate constant Kr, CSM divided by rho. Cs is the concentration, M is the molecular, and the density. So actually this is constant, so the delta, the thickness actually is but directly proportional with rate constant. Okay, and this is a show time. So when in the show time doing the reactions, the thickness of the dioxide layer will proportion with the rate constant of that in the wet method, or okay, in the wet method, so it will be the reaction control. But however, on the other hand, if the t plus tau is much larger, this is quite large, so 1, you can directly ignore the 1, and this is 1, so you directly take the root on this 1, so you got these results. So the thickness of silicon dioxide will be proportional with the square root of b times t 1/2. Okay? And what's the b? B is proportional with diffusivity, and the rest of part are the constants. So it can be rewrote as proportion with square root of d, t 1/2. So when we doing our experiments, we can measure the delta, thickness of dioxide, right, as a function of time. So what I'm going to, you can estimate what kind of graph or data you're going to get when you measure the thickness of silicon dioxide layer as a function of time. So in the beginning, it's directly proportional with the t, so it'll be shown like this. And for longer time, the delta is proportional with t to 1/2, will be like this. Sorry, so it'll be 1/2 here. Okay, so this diffusion control means the D actually is diffusion. So the thickness for a longer time, reaction time, the thickness of the dioxide layer is controlled by the diffusivity, square root of diffusivity. So we call it a diffusion control. So when I perform, I flow the oxygen, react with secant substrate to generate secant dioxide layer at specific temperature. When I measure the thickness as a function of time, I will get this curve. So in order to convince you, I grabbed some data from the literature. So for the dry method here, you can take a look at it's 800, 900, 1000 and 1100. So the thickness in the beginning is linear and become parabolic. And when you increase the temperature, you can observe the thickness is get thicker and thicker. Okay. So I can convince you in the shorter reaction time is linear, then become parabolic, rate constant. Okay, so in this regime, short reaction time is reaction control. So you can from this slope, B divided by A, as long as I fit it, I get the slope. I can get what's the KR. And the same idea, if I fitting for the long reaction time, I can get the diffusivity. So next, as long as you can get the KR and diffusivity, I can further get the activation energy, right? So talk about here, regarding to a rate constant, if you can get the KR at a different temperature and draw the log B divided by A is a log slope at different temperature. Then after fitting, you can get the slope is corresponding to activation energy for the wet method. So just a quick reminder, the rate constant is proportion with exponential negative activation energy divided by RT. So as long as I log the KR rate constant and versus 1/T, the slope is corresponding to activation energy. So this is the idea. So based on this, how to get this data, actually based on these results, I need to get the slope for this one, and this one. As long as I get slope, I log them and get and after fitting, I can get the activation energy. It's 2.0 eV for dry method. And for the longer, but this is for short time, right? For longer time, this regime, I also can log B or log D, doesn't matter, versus 1/T, and you also can perform at 3 or 4 different temperature. Then you can, after fitting, you can get the activation energy for diffusion process. So get this results. Okay. So this is we finish the wet method. The dry method. So let's move back to how about if the situation becomes to wet method. So the only difference is you just you substitute this gas as a water vapor, and the rest of part will be similar, right? But because it's water vapor, so concentration here probably you need to, and transport coefficient should be a little bit different. And also this part, because already be changed with the water vapor, so the low M should be modified, okay? But most part actually is remain constant on that situations, okay? So when I measure the thickness as a function of time for the wet method, and also I can see the linear regime and parabolic regime here. So for the linear regime, I also can perform the same idea, right? For a short time, and as long as I got the slope, then log the slope at different temperature, and after fitting, I can get the activation energy for the wet method. And here it's interesting, you observe the slope are similar, so which means the activation energy activation energy of reactions is similar for dry method and wet method. It's reaction, right? But it turns out reasonable, right? Because it was second bond. In order to get the second dioxide, for reaction parts, you need to break the second bond and replace to form a second oxygen bond, right? So no matter is use a dry method or wet method, the reaction part have a similar energy barrier. Because it's reaction, you need to break down the second bond. So energy barriers should be similar, it's reasonable. But when we move to the longer reaction time, it's diffusion control, and I perform the same idea. Then after fitting, I got the activation energy is smaller than that in the dry method. So each implying that the water vapor can diffuse faster in the oxide layer compared to that in compared to the oxygen. So due to here, we can say diffuse through the oxide layer, water vapor will be easily and diffuse faster in the oxide layer. So the growth rate will be faster. So the wet method can have a higher growth rate than that in the dry method for a long time reaction time. For a short time, actually it should be similar, okay? Because it's reaction control. Okay. So I'm going to give you a summary here regarding to the new term we call the transport coefficient, which to describe how fast the A molecules diffuse through the film layer. We use the transport coefficient. KL equals to diffusivity divided by the thickness of the film layer, delta X. And regarding to the heterogeneous reactions, when the reactants passing through different layers and reactions, as we can consider all process, we can consider they are series reactions. So the overall resistance will be the summation of each layers. So for example, like the overall resistance, which is reciprocal of K overall, equals to the resistance in transport layer 1 and resistance in transport layer 2, and plus the resistance of reactions. And that's the other quite important tips or tricks we always deal with is, under the steady state, the transport flux will be equal to reaction flux. That will help us to substitute the unmeasurable concentration reactants as a function of concentration reactants. Okay, so that will help us to get this to substitute unmeasurable terms. And when regarding to the time dependent of silicon dioxide thickness, the example we just showed you, in the short reaction time, how short it is, you need to satisfy these criteria. Then we find the thickness of silicon dioxide layer is proportional to the rate constant Kr. And for the longer reaction time, which satisfy these criteria, we find that the delta square will be proportional with the diffusivity. Okay, so this way people will call it as a linear rate constant, because if we draw the delta versus T, it's linear relationship, And if we try to draw the delta versus t here, it will be a parabolic relationship. So some people also call it as a parabolic rate constant. Okay, so today we ended here.